All right. Good morning, lads and ladies. Welcome, or I guess good afternoon. Welcome back to Cal 2. I apologize if you tried to come to my office hour earlier today. I got called into an emergency meeting, and so I had to bail on that. I know that sucks. But don't stress. I will have my normal office hour tomorrow, and if you do need to schedule additional time with me, you can always send me an email and request a one-on-one office hour. I have 5 hours
Was that
to that. So let's get.
was that meeting yesterday as well? Because I attempted to visit you in office hours yesterday and you weren't there.
No, I had my normal office hour yesterday. Yeah. Yep,
Okay.
normal office hour yesterday. I had like 10 people come through. It was quite busy.
Strange. Your link might not be working. I attempted to join your meeting at 1:30 and you weren't there.
That is strange. I can check my Zoom logs. Do me a favor, send me a message about that. Remind me, I'll check
Sure
the
thing.
Zoom logs. Did anybody else have problem joining the office hour yesterday?
Yeah, it was the same thing for me too. Like it didn't like open until like 1:40 or something like that.
That's very weird, but the link did work for you, right?
It did, but like it just said like waiting for the host to start the meeting for like 40 minutes.
That's strange. That is. Yeah, yesterday's office hour was normal and I did have a bunch of people come through. There might be some sort of like cap because it was a very busy office hour. Maybe for some reason there was like the waiting room bugged or something like that. But I'll look into it. That certainly should not be happening.
Okay, thank you.
Yeah, that's strange. Actually, Kaylee, I remember you being there. Yeah, we talked and I tried to get your attention a few times.
Oh yeah, because
with other students.
when I first went on, it didn't like let me in until like 1:40, I think. And then I didn't notice you calling my name because I was doing something and my volume was down. That's why.
That's okay. It's interesting though that on your end it didn't show you as being let in because on my end it did show you as being there.
For like 40 minutes.
15, I think. So there must have been something weird going on. I'll look into this, guys. I did have problems with Santa Fe IT this morning. I spent about 30 minutes with them on the phone trying to get my first Zoom meeting set up correctly. For whatever reason, it wasn't working. So I suspect there is something fucky going on in the background. But I'll check the logs from yesterday's office hour and see if that doesn't explain some of what's going on. And I'll send an email to SFIT to get it figured out. In the meantime, let's get moving with the last little bits that we need here. So today, we're going to finish section 7.2 on trig integrals. And then I'm going to introduce at the end of class here, I'm going to introduce a little bit this idea of Trig-Sub or trigonometric substitutions. So I mentioned this the other day. The reason we grind so hard on trig integrals in section 7.2 isn't just because trig integrals are themselves fascinating. It's also because for a lot of algebraic integrals, a lot of integrals where the integrand has nothing to do with trig at first, the only way to solve them is to make a substitution that turns them into trig integrals, and that's called Trig-Sub. So we really want to get good at these sine, cosine, and secant tangent integrals, not just for their own sake, but also because of what we're going to be doing in 7.3. So last time, we saw how to handle any integral of the form integral sine raised to some power x times cos raised to some other power. And we talked about integrals of the form some power of secant times some power of tangent. So the sine cosine integrals were completely resolved. If there is an odd power, then we're going to set one copy of the odd powered function aside with the differential, and try to do a U-sub for the other function. So if the power of cosine is odd, you set a cosine aside and substitute for sine. The idea being, since the cosine power was odd, when you pull one off, the remaining power will be even, and you'll be able to rewrite those using the Pythagorean identity in terms of the sine function. And you can switch the roles of sine and cosine there, and it all works great. If the power of sine is odd, you'll pull one copy of sine off to the side and try to substitute for cosine. Idea being, since the power of sine was odd, when you take one away, the remaining power will be even, and you can rewrite those using the Pythagorean identity as cosine. The secant tangent integrals are a little bit nastier because it's not the case that the derivative of secant is tangent, nor is it the case that the derivative of tangent is secant, which is what makes the sine cosine integrals so nice. The secant tangent integrals, though, do have a similar thing. There are Pythagorean identities relating secant to tangent, and it is true that the derivative of secant is the derivative of tangent is a power of secant, and the derivative of secant involves the tangent function. So some similar thing can be done here. I'm not going to recap the sine cosine integrals, but I'm going to lay out the secant tangent strategy. So we completed a few examples, and I want to lay out the strategy and then do one or two more examples. So strategy for integrals of the form integral secant mx tangent mx dx. We're going to break this into a few cases. If the power of secant is even, that's what allows us to substitute for tangent. If the power of secant is even, then we set aside a copy of secant squared x with the differential to help us substitute z equals tangent x, because we know that the derivative of tangent is secant squared. Since the power of secant originally was even, when you pull two of them off, the remaining powers of secant will be even. These can be rewritten as tangents using the second Pythagorean identity, tan squared x plus 1 equals secant squared x. All right, so this is our first kind of nice case for the secant tangent integrals. There is one other nice case here, and then there's a nasty case. The other nice case is if the power of tangent is odd. Right, so if the power of secant is even, we're in good shape. If the power of tangent is odd, we're in good shape. If the power of tangent is odd, then we set aside a copy of secant x tangent x with the differential to help substitute z equals secant x. So if the power of secant is even, we're going to substitute for tangent. If the power of tangent is odd, we're going to substitute for secant. Since the power of tangent was odd, when we grab one of the tangents off as a part of this secant tangent, the remaining powers of tangent will be even. And so those can be rewritten in terms of secant. The remaining even powers of tangent can be rewritten in terms, I should have a hyphen here, rewritten in terms of secant using the same identity, tan squared x plus 1 equals secant squared x. And so both of these will yield a polynomial. Right? Both of these are nice cases in the sense that you can make a little substitution and turn your integrand into a polynomial. And we saw one integral that we could do both of these two the other day. Namely, these are not mutually exclusive cases. It's possible that the power of secant is even and the power of tangent is odd. And in that case, you have a choice. Just like with the sine cosine integrals, where both powers of are odd, you have a choice. If the power of secant is even and the power of tangent is odd, then again, you have a choice. And you want to substitute for the larger power. That way you don't have to do as much algebra. I'd like to do one or two more examples like this. But before I jump into examples, I want to show you the remaining possibility here. This is the unpleasant case. If you're not in either of these cases, if the power of secant is odd and the power of tangent is even, then, well, we're kind of fucked. Then we'll use IBP. Some combination of trig identities and make the integral loop. So this is the rough case for the secant tangent integrals. I've burned through all my paper here, so I need to grab a little bit more paper, and then we'll look at some. All right. So I'd like to do one or two more examples that are not terribly hard, and then we'll look at one or two examples of this nasty case. So who can tell me which of those three cases this integral falls into, and how should we handle it?
Secant being even, so you can sub for tangent by setting aside a copy of secant.
Yeah, that's the game. So the power of secant is even, and I want to substitute for tangent. If I'm going to substitute for tangent, I'll need a copy of secant squared to set aside with the differential. And the nice thing about this is that when I grab two of these secants to put over here, I have an even power of them left. So this can be rewritten in terms of tangent. And I want to do that before I substitute so I can see exactly how my substitution will go. Since tan squared plus 1 is secant squared, this is just tan squared x plus 1 times tan squared x times secant squared x dx. And now I'm ready to make my substitution because this is a polynomial in tangent, and this is exactly what I need for the differential. So if z is tangent x, then dz is secant squared x dx. And under that substitution, this will become z squared plus 1. This piece right here will become z squared. And secant squared x dx is exactly dz. So we really do get a polynomial. Now to integrate this polynomial, I need to rewrite it in standard form. I need to distribute my z to the 2 here over these parens. And I'll get z to the 4 plus z squared dz. Now I can integrate using my power rule. This is z to the 5 over 5 plus z to the 3 over 3 plus a constant. And then finally, we go back to our original variable. If it was a definite integral, I would change my bounds here, and I don't have to go back to the original variable. But I'm doing these as indefinites. So this would be the 5th power of tangent x over 5 plus the 3rd power of tangent x over 3 plus c. So these are not too bad. Any questions on what we did here or how we knew to do it? All right. Let's try something else then. What if I want to integrate the 5th power of secant times the 3rd power of tangent? I ask, is the power of secant even? No. So we're not going to substitute for tangent. Is the power of tangent odd? Yeah. So I can try to substitute for secant. And if I want to substitute for secant, the thing I need to set aside is secant tangent, because that's the derivative of secant. So I'll grab one of these and one of these. That'll leave me with the 4th power of secant times the 2nd power of tangent times secant x tangent x dx. And the neat thing is that no matter what this odd power was here, if this was a 3 or a 31, then when I take one of those tangents out, the remaining tangents will always be even. So I'll always be able to rewrite these in terms of the secant function. Let's go ahead and rewrite that tangent as a secant. So this is secant to the 4 times tangent x is secant squared x minus 1. And we want to be really comfy with these identities. So tan squared plus 1 is secant squared, which means that tan squared is secant squared minus 1. And the order of the subtraction does matter. And then we still have secant x tangent x dx. So from here I have a polynomial in secant times exactly what I need to substitute for secant. So that's what we'll do. We sub z equals secant x. dz is secant x tangent x dx then. And so this integral becomes integral of z to the 4 times the quantity z squared minus 1 times dz. And again, we'll just distribute and integrate, not bad. So this is going to be z to the 6 minus z to the 4 dz, which is going to give me z to the 7 over 7 minus z to the 5 over 5 plus a constant. And going back to my original variable, I'll have the 7th power of secant over 7 minus the 5th power of secant x over 5 plus c. So these are the nice ones. Even within these nice categories, there can be some problems that look a little iffy. So before I jump to one of the really nasty guys, I'd like to look at one or two kind of special cases here that aren't entirely obvious, and maybe a problem or two from the homework. Questions on this before I move on?
Wait 1 second.
Sure. Okay.
Okay, thank
All right. So one of the ways that these things can look a little bit weird, but still be within our kind of nice categories there, is if it's not immediately obvious where to get the extra bits from. And I'll show you what I mean by that. If I wanted to integrate the 6th power of, let's use a different variable just for fun, secant theta. Here it's certainly true that the power of secant is even, but there aren't any tangents floating around. So the idea of subbing for tangent sounds a little weird, right? Like, why would you substitute for tangent? That's what our strategy says that the power of secant is even. We're going to substitute for tangent. But why would I substitute for tangent in an integral that doesn't have any tangents?
Could you pull out a secant squared and then use the Pythagorean identity to turn it into tangent?
That's exactly the move. So we still just kind of trust that strategy, right? We trust that what we said there was true and we can make it work. So I'd begin by writing this as the 4th power of secant times secant squared x dx, still just trusting that because the power of secant is even, I am going to substitute for tangent, which means I need to set aside a secant squared. Still no tangents here.
You said d theta.
Oh, shit, I'm
Yeah,
so
we started.
yeah, habits. All right, let's do it down here. Thank you, thank you. Yeah, secant to the 4 theta times secant squared theta d theta. Thank you, thank you. So we're still thinking of substituting for tan theta, even though there aren't any tan thetas here to mess with. But the remaining even powers of secant can be rewritten as tangents. So this is secant squared theta squared times secant squared theta d theta. And now within here, I can re-express this as a tangent. So tan squared theta plus 1 equals secant squared theta, which means secant squared theta is tan squared theta plus 1. All of that is squared, and now I have here my secant squared theta d theta. This looks like it's ready for the substitution, even though the original integral really didn't look like it was ready for a tangent substitution. So here I could let z be tangent theta. dz will be secant squared theta d theta. And we're ready to rock and roll. This will be z squared plus 1 quantity squared dz. And just like all the other problems we've done like these, we'll FOIL this out and use the power rule. So that's going to be z to the 4 plus 2z squared plus 1 dz, which will integrate to become z to the 5 over 5 plus 2z cubed over 3 plus z plus a constant, which is the 5th power of tangent theta over 5 plus 2 times the 3rd power of tangent theta over 3 plus tan theta plus a constant. Not too bad, right? The other way this can look weird, right? We said, all right, one of these strategies is dictated by the power of secant, and it involves the tangent function. The other one is dictated by the power of tangent and involves the secant function. So what if I just have a raw odd power of tangent, like tan cubed or tan to the 5th? And I think one of your homework problems is of that nature. So let me pop up your homework here. And we can take this next example from there. So I have a straight odd power of tangent here, right? 10 squared, 10 secant. Yeah, let's try 10 to the 5th. Has anybody had any success with this? Any ideas what we can do here?
We can pull out another 2 tan, which leaves n being odd. And then we can substitute for secant.
Let's try that. Yeah, let me grab 2 copies of tangent out, leaving 3 copies of tangent here. And then that tangent squared, I can replace him with his Pythagorean equivalent. Tangent squared is secant squared minus 1. Now remember, our high-level goal, if the power of tangent is odd, is to substitute for secant, right? But now things have changed. I could split this up, and there's more than one way to do this. I can split this up as secant squared x times tangent cubed x minus tangent cubed x dx. And this integral I can handle, I think, the way Alexander was suggesting. I can substitute for tangent here. The differential secant squared is right there. But I still have to manage the cube of the tangent function. So let's split this integral. Let's treat this as the integral of tan cubed x times secant squared x dx minus the integral of tan cubed x dx. In this integral, I can make the substitution z equals tangent x, and dz there would be secant squared of x dx. So he's going to become integral of z cubed dz But this integral isn't as clear. In fact, he has the exact same problem that the original integral had. It's just a raw odd power of tangent. So if we trust this procedure, we can try the same sort of thing. I can say, okay, this would be tan x times tan squared x dx. And I can write that as tan x times secant squared minus 1. And then I'll be able to split him into a couple of integrals. One where I'll again substitute, and then just a blank power of tangent. So let's see where we are here. When I integrate z cubed, I'll get z to the 4 over 4. I'm going to leave off my plus c here, and I'm going to be really careful about my notation. I'm not going to claim that the whole original problem is equal to this, because it's not. It's this combination of things. This piece is going to become the 4th power of tangent over 4. And over here, I'll have integral of tan x times secant squared x dx minus the integral of tan x dx.
Wait, but if we're substituting for tan x, then couldn't we just turn the tan 3 into an z to the 3rd power?
I'm only making that substitution in this integral because it's only in this integral that I have the secant squared that I need to make that
Okay.
substitution.
Well, what
This
happened to
guy's
make
not
them
ready
separate
for that.
integrals? It just seems like you distributed.
Well, I split up the integral from here to here. I wrote the first piece as the integral of this minus the integral of this. So
I
going
just
from
don't understand why you would do that if you could substitute for both the tangents at once.
I cannot. I cannot
can't.
substitute for both the tangents at once because this does not have a factor of secant squared. Right? I cannot grab a secant squared out of this whole thing to set aside with dx.
Hmm.
I only have a secant squared here attached to this part.
Okay, I see.
That makes sense? Now, if we're thinking ahead a little bit more in this stage, rather than splitting up, I could split this as tan times tan squared, and then grab a secant squared out of at least one of those parts and do this piece together with this piece. But at this stage, I'm not ready to substitute in the whole integral because I don't have a factor of secant squared I can pull out of the whole integrand. You can think of it like, what if you solve this for dx? You'd get dx equals 1 over secant squared x times dz. The secant squared would cancel here, but it wouldn't have anything to cancel with here. So we really do need to split this up in order to make that substitution, at least unless we're, without rewriting this and doing considerably more algebra there. So if we're just kind of following our notes, just kind of following the pattern that we've seen, this is the more natural thing to do. And if we were looking far enough into the future, we could see that, yeah, I could probably grab a secant squared somewhere in here. But in the same way that we were just able to peel off one of these and give them a secant squared, we're just going to be able to peel off one of those and give them a secant squared. We're going to have that same problem again. So this first piece, which is the integral of secant squared times tangent cubed, is going to be tan to the 4. This piece, I'm going to make that same substitution. I'll use a different variable here because I don't want us to confuse things. So I'd make the substitution w equals tan x here. dw is secant squared x dx. And this time I'm just making the substitution in this middle integral. So here I would have minus integral w dw. And the integral of tangent over here is still hanging on. So at this point, I have tan to the 4x over 4 minus this integral minus this integral. And this line really is equivalent to my original. When I integrate the w dw, I'll get w squared over 2, which is, I'll just write it like that for now. And then I still have my minus integral tangent x dx. That w is going to be a tangent. So I get to this line, I'll have the 4th power of tangent over 4 minus the 2nd power of tangent over 2 minus, what's the integral of tangent itself? Does anybody remember this one?
ln of sine.
Almost.
Oh,
ln absolute
secant.
value secant x.
There's a few ways to write it. Yeah, you can write it as negative natural log of cosine x. And at this stage, I should put in my plus c because I don't have any more integrals. Or you could write it as the positive natural log of secant. Either one is fine. I'll do it like this because this is the more natural way for this to drop out. If you want to see where it comes from, the substitution is u equals cos x. Du is negative sine x dx, and you have to rewrite the tangent as sine over cosine to make this go. But the result is this, and this really is one we should know, right? This was one of our 6 fundamental trig integrals from Tuesday's class. So this guy at the end of the day here is going to be the 4th power of tangent over 4 minus the 2nd power of tangent over 2 plus the natural log of the absolute value of cos x plus c. And I'd like to challenge you guys to find another way to do this integral. This isn't the only way to do this.
Can we sub for secant instead of subbing for tangent?
There is a way to get through this with a secant substitution, but it requires a little bit of love. So I encourage you to look for alternate substitutions. There's actually 2 other ways to do this. One of them is with a secant substitution. And then there's another way to attack this using u sub just by grouping terms and being a little bit more clever with your trig identities. But your answers will come out equivalent to this, right? Up to an additive constant. Questions on what we actually did here? Questions on how we got through this? It might not be the most elegant way, but I do think this is the most natural way to proceed. Okay. Let's take one more from the homework. We'll come back to this. This is a good problem. But let's do one that's a little bit clever here. I'd like to do a definite integral if we can. I'd like it to be not entirely obvious how to proceed. More definite integrals in here. Cotangent squared is kind of cute. Cotangent cubed. This one is fun. But it's hard to do as a definite integral. Do I have any other definite integrals in here? Those, yeah. All right, we'll do one early one just to make sure we're getting a definite integral example in, and then I'll come back and do the funny reciprocal of cos x minus 1. Let's look at this. I want to integrate from 0 to pi over 2, the 7th power of sine times the 5th power of cosine. I have some choice here, right? Because both of those powers are odd. In order to minimize the algebra I have to do, I'd like to substitute for sine theta, which means I'm going to set aside a copy of cosine and rewrite the remaining cosines as sines. So I'll leave the 7th power of sine alone. I'll grab one of the cosines, leaving 4 of them here. And then those 4 cosines that are still hanging out over there, cos to the 4 is cos squared squared. I'll say it over here. Cos to the 4th theta is the square of cos squared. So this is 1 minus sine squared theta all squared. So here I'll have the 7th power of sine times 1 minus sine squared theta all squared times cos theta d theta. Now when I make my substitution, it's just like it was in the previous examples, but I need to make sure to change my bounds. So I'm going to substitute z equals sine theta, which means dz will be cos theta d theta. That's why we set that aside. I also need to figure out how do these theta values of 0 and pi over 2 give me z values. So when theta is equal to 0, z would be the sine of 0, which is 0. And when theta is equal to pi over 2, z would be the sine of pi over 2, which is what?
One.
Good. So my old integral ran from 0 to pi over 2. Those were theta values. My new integral is going to run from 0 to 1. Those are z values. So my new integral is a 0 to 1 integral. And I'll have here z to the 7 times 1 minus z squared times dz. And from here, it's the same as these other problems. I'm going to try to conserve paper a little bit by writing over here my z to the 7. It's going to have to hang out while I distribute 1 minus, or FOIL out 1 minus z squared. That'll be 1 minus 2z squared plus z to the 4 dz. And that'll be integral 0 to 1 z to the 7 minus 2z to the 9 plus z to the 11 dz. My antiderivative is z to the 8 over 8 minus 2z to the 10 over 10, which is z to the 10 over 5 plus z to the 12 over 12. And this is to be evaluated from 0 to 12. At the lower bound, I don't get anything. And if I plug in 0 for z here, everything stays 0. At the upper bound, it's going to be 1/8 minus 1/5 plus 1/12. So that's our answer here, 1/8 minus 1/5 plus 1/12. And as far as I'm concerned, you can leave it like this. I'm not here to test your arithmetic skills, and I certainly hope you won't judge mine. But if you wanted to, you can combine those, have a common denominator, all that good stuff. Any questions on this problem?
How did you know to use Pythagoras and not half angle?
Because I had odd powers. So I was beginning with odd powers, and that tells me my strategy at the start is going to be to use U-sub and Pythagoras. So if in the sine cosine integrals, any of the powers are odd, then my kind of high level strategy is Pythagoras and U-sub. If at the beginning of the sine cosine integral, I have no odd powers, then I have to use the half angles.
Can you show an example today of the half angles?
Yeah, sure, we can do another one of those. There is one nightmare half angle problem in your guys' homework set. I don't know if you've gotten to it yet, but number 4 here is actually pretty savage. Yeah. So we can run through this one if you guys really want to. Let me get some lotion, massage my hand for a minute, work the calluses, you know, all that good stuff. This is just life. Let's do it. The funny thing about definite integrals of sine and cosine where the powers are both even, the thing that's kind of most frustrating about these is that usually the whole result comes from one term. You'll end up with like 6 terms and all of them are meaningless except for one of them. You'll see what I mean as we go through this. So we're going to do the integral from 0 to pi. I'm going to ignore the 3 if you don't mind. Sine squared t times cos to the 4t dt. And then I do want to go back and look at that 1 over cos x minus 1 integral. That's a good one too. All right, so to do this guy, since we don't have any odd powers, our strategy tells us we're just going to beat this to death with half angle formulae. Those half angle formulae are cos squared theta equals 1/2 1 plus cos 2 theta, and sine squared theta equals 1/2 1 minus cos 2 theta. And I'm going to write them using that variable here so we can make some adjustments as needed. I begin with the observation that cos to the 4 is cos squared squared. So this is the integral 0 to pi sine squared t is 1/2 1 minus cosine of 2t. And then cos to the 4 is going to be 1/2 1 plus cos 2t all squared dt. Because cos to the 4 of t is cos squared t squared, which is, you know, the 1/2 1 plus cos 2t squared. When you square a product, right, I've got a 1/2 times the quantity 1 plus cos 2t. You square each term in the product. So this is integral 0 to pi 1/2 1 minus cos 2t times the square of 1/2 is 1/4, and the square of 1 plus cos 2t is the square of 1 plus cos 2t, like this. This problem can get more nasty or less nasty depending on how you choose to do the algebra here. So I'm going to show you a little trick.
Can you do different squares?
Yeah.
So you
Oh, exactly. If you take the first term there, the 1 minus cos 2t, and combine it with the first of the other two, then that looks like a difference of squares type thing. That's exactly the idea, yeah. So let's pop out the 1/8. I have integral 0 to pi, and I'll write this as 1 minus cos 2t times 1 plus cos 2t times 1 plus cos 2t dt. And I choose to multiply the first two first. All right, we're gonna have to multiply everything out. But if I do these two first, then the algebra gets less out of hand. You have less terms to track, and it's just easier to manage. So this looks like a difference of squares, and it is. It's 1 minus cos squared of 2t. So I have that, and I also have 1 plus cos of 2t. Still chilling. Now you can check, the cross terms cancel, right? Minus cos 2t times 1 and plus cos 2t times 1. Those will cancel. So you really, this is a difference of squares. Now I have to distribute these. There's no escaping that. So my firsts and then my outers will be minus cos cubed 2t. I'm sorry, those are my lasts. Minus cos cubed 2t. My outers will be plus cos 2t. And my inners will be minus cos squared 2t. Sorry for the weird order there. And you know, one of these things is not like the others. Cos 2t, I know how to integrate this. He's done. 1, not worried about him. Cos squared 2t, more of the same, right? More half angle shit. Cos cubed 2t, be different. That's an odd power. So I'm going to split this up. In my next step here, I'll do a few things. I'll write this as 1 plus cos 2t. This guy I'll replace by his half angle equivalent, which is 1/2 1 plus cosine of 4t. And then this guy, I'll just move him to the end, minus cos cubed of 2t dt. So if you're looking like what piece went where, this piece is this guy, and this guy came over here. The first three pieces I'll leave in one integral. This guy I'm going to split off. He's different, meaning he requires a different method than the remaining pieces. Specifically, I'm going to make a substitution to integrate him, and that's not a substitution that I want to make in any of these. Before I proceed with the first three terms, I'll distribute the negative 1/2. That gives me 1 plus cos 2t minus 1/2 minus 1/2 cos 4t. And now I'm going to give the other integral, the other piece, its own integral. This constant needs to come along. That 1/8 belongs to the whole thing, right? That's why we always write these in parentheses, because the constants out front and the differentials at the end really do need to be thought of as distributing through. So this is the nice move here. In the first integral, I can combine the negative 1/2 and the positive 1 here because they're both constants. Everything else is micro u sub. This is micro u sub the sine 2t over 2. This is micro u sub the sine 4t over 8. This guy is not a micro u sub. This guy, we have to go back and think, okay, how do I integrate a raw odd power of cosine? Well, it's an odd power, so I'm going to grab one, set to the side, and make a little u sub. Not a little u sub, like a regular u sub. First, let's do this. Let's combine our like terms. That makes life easier. 1 minus 1/2. This guy combined with this guy gives me positive 1/2. Then plus cosine of 2t, and then minus 1/2 cosine of 4t dt. And then over here, I'm going to get ready for my u sub. I'll write this as cos squared of 2t
So what?
times cos of
Like a while.
2t dt. So this is where we're at now. And again, this first integral, I know how to cook up antiderivatives for all of those pieces with my eyes closed. This guy requires an actual substitution with some effort, and I'm going to change my bounds here when I do that sub, the real sub. Yeah, I might go ahead and mute that. Sorry. So, antiderivative time here, u sub over here. The antiderivatives from the first piece will be 1/2 t plus sine 2t over 2 minus sine 4t over 8. And this all gets evaluated from 0 to pi. The 8 here is coming from the 4 with the micro u sub and the 1/2 that was out front. And in the second integral, I'm going to make a substitution, a real substitution, not a micro one. Z equals, it looks a little bit weird here, sine of 2t. Maybe let me do this on the next page. So for now, I'll just copy this down. We'll look at the substitution on the next page. Cos squared of 2t, I rewrite as 1 minus sine squared of 2t, right? That's the substitution I'm thinking of making there is for sine. Cos 2t dt chilling. Okay. And the reason I'm doing this is because this is just how we handle integrals of odd powers, right? You set one copy aside over here, rewrite everything else in terms of the other function, and then you substitute to turn this piece into a polynomial, and this piece will be your differential. Something funny is going to happen here. It's something we've seen in class before, but I'll go through it. Something funny happens over here too. When you plug 0 in, all this shit is 0, right? 1/2 times 0, sine of 2 times 0, that's the sine of 0, so that's 0 over 2. Sine of 4 times 0 is also the sine of 0 over 8, 0 over 8 is 0. When you plug in pi, sine of 4 pi is 0, the sine of 2 pi is 0. So among these 6 terms you get when you evaluate this between 0 and pi, the only one that is non-zero is this one, and only when you plug in pi. It gets better. Let's see what happens when I make the substitution over here. The substitution is for sine 2t. dz then would be 2 cos 2t dt. So I'd get another 1/2 out. But the funny business is with the bounds. When t is equal to 0, z would be the sine of 2 times 0, which is 0, okay. When t is equal to pi, z would be the sine of 2 pi. What's the sine of 2 pi?
0.
Also 0. Notice that my lower bound and upper bound are the same after this substitution. This whole thing is 0. So what do I get? I get 1/8 times 1/2 pi plus 0 minus 0. And then when I plug in the lower bound of 0, everything over there is 0. There's the first piece. Minus 1/8 integral 0 to 0, 1 minus z squared times 1/2 dz. The integral from 0 to 0 of anything is automatically 0. This is equal to 0 because integral from a to a of f of x dx is always 0. So how many terms did we have here altogether? If we carried out the antiderivative step here, I would have 2 terms from this, 3 terms from this, so 5 terms altogether, all to be evaluated between 0 and pi, a total of 10 pieces that need to be evaluated. Of those 10 pieces, 9 of them are 0. The only one that gives you any actual contribution is this. So the answer is pi over 16. That's what I mean when I say these even powered integrals are kind of annoying, right? You do a lot of work, and then the result shakes out from this tiny little part. Everything else gives you nothing. This is coming from the orthogonality of sine and cosine. This is something we talked about briefly in class the other day, and that's why I mentioned that. So when you integrate sines against cosines, it's often the case that most of the terms come out to be 0, especially when you integrate over a full period or a half period, like 0 to pi.
So if you integrate any function from a to a, is it always 0?
Yes. Yep, the integral from a to a of any function is always 0. You can think about it in terms of areas. What's the area underneath that function from 0 to 0? If you don't have any width, you can't possibly have any area.
What if it's not defined at that point?
There are some weird cases involving like the Dirac delta function, if you've ever heard of that, where you could, in theory, have a very narrow, infinitesimally narrow window of integration and still get a non-zero answer out. But even in those cases, if your function exists, then the answer is definitely 0. The Dirac delta function isn't technically a function. And so in a limiting case, you could say if your function value is infinity at 0, then the integral from 0 to 0 of your function could potentially be non-zero. But this is a polynomial. We don't have any issues like that here. This polynomial from 0 to 0 clearly encloses no area. It's well defined. There are extreme cases there, but they require measure theory to really understand, and we will not bump into any of them in this class.
And then my second thing that I noticed on this problem that I hadn't known before was that the Pythagorean identity works even if it's not like cos of x. It works with like cos squared of 2x as well.
Yep. Pythagorean identities don't care what the inside is. Sine squared of anything plus cos squared of that same thing is always 1. So the inside can be whatever you want, as long as the insides here match the insides here. That's a neat thing. This is kind of what we mean by identity, is that it's not particular on what's inside. It's true for all values of the function, which means you can substitute whatever you want into those identities and you will still get a true statement. Other questions or comments on this one? I think of this as like the dad joke of integrals, you know, because you got all this like hairy dog buildup, and then nothing at the end. As an indefinite integral, it's still very challenging. It's still very worth doing. As an indefinite integral, this would not be trivial. You wouldn't get a bunch of zeros. You would actually get meaningful pieces out of every part here. And that would be challenging. But you'd go about it the same way.
So that means that with different bounds, you would also have to have every piece. It's just because it's a 0 that makes it none of it matter.
The 0 and the pi are both conspiring here to make a lot of these terms 0. If I made this a pi over 6 and this a pi over 4, then all of a sudden you got a lot more work to do.
will there ever be problems on tests where we don't have bounds that make unit circle easy?
No. Yeah, the only values of trig functions I will require you to summon will be those that you know from the unit circle. There may be times where I need you to carry around a term like the cosine of 1 or the inverse tangent of 2. But in those instances, you can just write them as cos of 1 or inverse tangent of 2. I don't expect you to magically simplify or know those values. The only time I'll expect you to substitute in and work with those things is the values you know from the unit circle. So good questions. Any other questions coming to mind? Okay, we have just enough time before our little break here to look at that last problem from the homework that I wanted to work as an example today. And we will take a few minutes and reconvene for lab. Anybody try this one yet? The integral of the reciprocal of cos x minus 1.
No, I haven't been able to try it. I don't know if I can fully understand that one yet.
It's not obvious. It's really not. I want to start with a warning. We know that 1 over a minus b is sure as shit not 1 over a minus 1 over b, right? This sort of algebra doesn't work. This is not a true statement. We can't do that. So this is not like secant minus 1.
Damn.
But we know that 1 minus cos x times 1 plus cos x is something nice, right? This is that same sort of difference of squares thing that we made use of to simplify the algebra in the last problem. This is 1 minus cos squared x, which is the same as sine squared x. So if I want to clean up this integral, I can multiply top and bottom, whoop, cos x minus 1, like that, times cos x plus 1 over cos x plus 1, like this. I want to introduce this factor downstairs because I know that will let me rewrite the bottom as sine squared. And once I get rid of the addition or subtraction downstairs, I just have a single term downstairs, life gets much better. So here I would have integral cos x plus 1, that's my top, divided by cos squared of x, and then plus cos x minus 1 dx, like this. Another interesting algebra fact when you change the order of subtraction in a binomial, it negates the binomial. So cos squared minus 1, another way to say this is, so what do we have here? We know that sine squared x plus cos squared x is equal to positive 1, right? So if I subtract the 1 over, I'll get 0. And then if I subtract the sine squared over, I'll get cos squared x minus 1 equals negative sine squared x. So we know 1 minus cos squared is sine squared. So you could deduce either through this fact or by just hunting around in Pythagoras that cos squared minus 1 is negative sine squared. That's the trick for this. This is a nice problem. Now from here, this negative downstairs, this is a factor of -1. So this will be negative integral cos x plus 1 over sine squared x dx.
And then you have cosecant, cotangent, yeah?
Yes. Well, not quite. Something like that. So here I'll have a cosecant cotangent. Here I'll have a cosecant squared. I need to split it up. There will be a cosecant cotangent.
That's what I meant, yeah.
Yeah, okay, good. Yeah, so we'll have cos x over sine squared x plus 1 over sine squared x dx. And then just like Alexander was saying, the slick way to handle this, you can split this up and do this integral as a u sub, and then rewrite this as a cosecant squared. But the slick way to do this is to rewrite everything in terms of cosecant and cotangent. So cosine over sine is cotangent. 1 over sine is cosecant. So that first piece is cotangent times cosecant, or cosecant times cotangent. And the second piece here is cosecant squared x dx. And then if you're really feeling like you got your tongue planted firmly in your cheek, you push the negative back in. So this is the integral of negative cosecant x cotangent x minus cosecant squared x dx. And then we ask ourselves, who has derivative negative cosecant cotangent, and who has derivative negative cosecant squared? In other words, now we're ready to handle this piece and this piece independently.
Cosecant is negative cosecant cotangent.
Good, yeah, the derivative of cosecant is negative cosecant cotangent. So the first piece is cosecant x. And whose derivative is negative cosecant squared?
Is it tan?
Cotangent.
That's what I meant. That's what I had in my head, because tan is secant squared.
Right, exactly. And that's the trick for remembering the derivatives of the cofunctions. They follow the same patterns, you just have a negative. So the derivative of secant is secant tangent. The derivative of cosecant follows the same pattern, cosecant cotangent, but it's a cofunction, so you'll have a negative out front. So the derivative of cosecant is negative cosecant cotangent. And similarly, the derivative of tangent is secant squared. So the derivative of cotangent should be like cosecant squared, but again, because it's a cofunction, you'll have a negative there. So yeah, derivative of cosecant is negative cosecant cotangent. So the integral of negative cosecant cotangent is cosecant. The derivative of cotangent is negative cosecant. So the integral of negative cosecant squared is cotangent. That's our game, and we're done. But this is a fun integral. It is. I like this one. And the neat thing for you to research independently, if you're curious, is just how much harder this integral gets if you change the 1 at the start to a 2. There is a magical substitution that I am not officially allowed to require you guys to learn, called the Weierstrass substitution, that I want to just describe for a second before our break. So what about integral 1 over cos x minus 2 dx, or other similar things? If I start fiddling with the constants in this integral, these are capital H hard, but a man named Karl Weierstrass, after whom I really wanted to name my dog, but nobody was on board with calling him Weierstrass, came up with a substitution.
Is it the tan x substitution?
Yes. U equals the tangent of x over 2. So this is called the Weierstrass substitution. And the Wikipedia page on it is actually very good. So the last thing I'll show you before we take our little break here is the Weierstrass substitution. It's a gnarly thing, right? So you let your new variable be the tangent of your old variable over 2. This has the effect of replacing any function of sine x and cos x by an algebraic function of t. Very shocking, not at all obvious. Named after Weierstrass, Euler fucked with it a little bit. Spivak called it the sneakiest substitution in the world. And it's got a great history and a great geometric interpretation, which, yeah, here we go. Here's a nice geometric interpretation of the substitution. This is capable of doing all sorts of things, like what I was saying. If you start fucking with the constants in that integral, this is really the only way to handle it, short of methods from complex analysis, which are much more complicated. So I encourage you guys to research this. You're not required to know it. Really, in order to implement it, you need to remember these facts, which are not easy, and it's not necessary for you to complete this class, but it is a good thing to know. It provides a fresh attack for secant and cosecant, which are not really satisfying, right? You remember how we did the secant integral? We multiply by secant plus tangent over secant plus tangent. It just feels kind of unsatisfying and shitty. Well, here's another way to do it, right? This Weierstrass substitution will do this for you. And also, it will handle integrals like this, which are very, very hard otherwise. Integrals like this, 1 over 2 plus cos x, is leading us towards something called an elliptic integral. And I will talk more about elliptic integrals when we get to them. I don't think they mentioned it on this page. And probably the wiki page for this is a little bit too intimidating to really get into. Yeah, some examples, stuff like this, right? Stuff like this. They're hard. They're really, really hard. But I'll show you 1 or 2 examples way down the road. For now, I would like you to just focus on fiddling around with the problems that are in the homework. There's enough in there to kind of give you a feel for what to do. And if you are interested in a deep way at all in mathematics, I strongly suggest that you work every problem in section 7.2. They're all really good. They're all really important. And there's a lot of deep stuff there that you can kind of start to get a feel for by working with trig integrals. That's where I'm going to leave the lecture for today. We're going to take a little break. We'll come back and do a lab. The lab today isn't going to be super long. I'm going to introduce the idea of Trig-Sub, and then I'll let you guys go. So 15-minute break, then we'll come back for about a 30-minute lab, all right? All right, see you guys in a little bit. Hey, Kermit, how are you doing? Looking pretty handsome, my brother. are we doing on time? We still got a little bit, right? Yeah, okay. I'm going to turn my share off for a minute, into some emails. We will come back here in just about 3 minutes and get started.
So Professor, is your office hours for tomorrow open? Oh, he may be away from his computer.
No, I'm still here. I'm just answering emails. Yeah, office
no
hours
problem.
tomorrow should be normal, 1 to 2 p.m.
All right. This lesson in particular is some mind magic that's very hard to wrap my head around.
The trigonometry stuff can feel pretty magical, but it's all about getting comfortable with the identities.
Yeah, mostly it's just hard to see the patterns of execution when you start a problem.
It's true, and I think a lot of it is kind of about playing around with things and sort of getting used to seeing what works and what doesn't work.
This is true. This is true.
But the more you play with them, you know, and it can be fun to work these problems with a friend. If you guys, I really encourage you to, you know, talk to each other and spend a little bit of time comparing what you've tried versus what other people have tried, and kind of think of it as a puzzle that you get to solve together.
I hear you.
All right. So let's start reconvening here. I'm gonna turn my share back on. We'll get back into the swing of things. I don't think I actually took a second to say this. I do want to apologize to anybody who tried to come to the office hour and wasn't able to get a hold of me. I know how frustrating that can be, and I just want to offer you a genuine apology. But with that out of the way, let's return to the content. And if there are burning questions that we wanted to ask in office hours, we can ask them here, of course, too. And before we get to that, I want to offer a little bit of motivation for what we're going to be doing next. Let me get this thing to focus. So by now, we're becoming pretty comfy with integrals of trig functions. This is good. Because a lot of hard integrals are best solved by turning them into trig integrals. And I want to begin with an example that can be solved purely geometrically. Consider the integral from 0 to 1 of the square root of 1 minus x squared dx. It's worth noting that the square root of 1 minus x squared is very much not the square root of 1 minus the square root of x squared. In other words, it is not 1 minus x. Square roots don't split up over addition or subtraction. This is actually a hard integral if you approach it from the FTC2 perspective, if you approach it from the perspective that we've been using, where you find an antiderivative. There is a perspective from which this integral is quite manageable. What we're doing there is we're looking for the area under the curve y equals square root of 1 minus x squared, right? This can be re-expressed as y squared equals 1 minus x squared, which can then be re-expressed as x squared plus y squared equals 1, which we should all recognize as the equation of the unit circle. So really what's going on here, where's my good purple pen here? This part, the upper semicircle, which I'm putting in purple here, hopefully you can see that color. This is y equals the positive square root of 1 minus x squared. And this part down here, which I will put in orange, this is y equals the negative square root of 1 minus x squared. So the area under the square root of 1 minus x squared from 0 to 1, which is the integral we're trying to calculate, is this area. So by geometry, the integral from 0 to 1 of the square root of 1 minus x squared dx, this is 1/4 the area of the unit circle, which is 1/4 pi times the radius squared. The radius is 1, which is pi over 4. So there it is. There's that integral, which from a fundamental theorem of calculus perspective is quite hard, right? You're not going to have any sort of easy time coming up with an antiderivative for this function using any of the methods we've discussed so far, including integration by parts. IBP won't help you here. However, it's not impossible. It just requires an introduction of geometric ideas. X squared plus y squared equals 1, being the unit circle, is equivalent to a certain trigonometric idea, a certain trigonometric identity, namely cos squared plus sine squared equals 1. So imagine for a second that I want to say trig up the integral. I want to make this triggy. One way I could do that is by substituting x equals sine theta. I could also substitute cosine theta. If I substitute x equals sine theta, then as always, I need to calculate a differential. The derivative of sine theta is cos theta. So my differential here would be cos theta d theta. And as always, I would need to change my bounds. Now here, the weird thing is that normally I let z be some combination of the old variable. But here, my new variable is on the right-hand side, and it's stuck inside the trig function. So I'm letting my old variable be equal to some combination of my new variable, which is weird. It's backwards from the way we normally do things. When I go to change my bounds, my old lower bound was x equals 0. My old upper bound was x equals 1. I need to solve for theta. So when x is 0, what's theta? When x is 1, what's theta? I'll do this off to the side here just for once. When x equals 0, we have 0 equals sine theta, right? Because x equals sine theta is the substitution I've made. So I will take the inverse sine of both sides to get theta. And the inverse sine of 0 is 0. So you need to know your inverse trig. And similarly, when x is equal to 1, we have 1 equals sine theta, which is the same thing as saying the inverse sine of 1 is equal to theta. And the inverse sine of 1 is pi over 2. So pi over 2 is theta. So when x is 0, theta is 0. And when x is 1, theta is pi over 2. And this is my little substitution box. Under this substitution, my integral would become, we'll write it here, integral 0 to 1, 1 minus x squared dx would become integral 0 to pi over 2, square root of 1 minus, well, x is sine theta, so this would be 1 minus sine theta squared. And then dx is cos theta d theta, so this would be times cos theta d theta. The miracle here is that the square root is going to become very nice. And that's going to be a consequence of the Pythagorean identity. This will be integral 0 to pi over 2 square root of 1 minus sine squared theta times cos theta d theta. And you know that 1 minus sine squared theta is cos squared theta. So this will be the square root of cos squared theta times cos theta d theta, like this. And then finally, the square root of cos squared is cosine. So this is the integral from 0 to pi over 2. I left off the 2 up here. 0 to pi over 2 cos theta times cos theta d theta. Now the truth is the square root of cos squared theta is the absolute value of cosine. But for the purposes of these problems, we will assume that you can ignore the absolute values. In other words, when we're doing these as definite integrals, we'll always use bounds that ensure cosine is positive. When we're doing them as indefinite integrals, it will always be this understanding that we're not terribly worried about the absolute value. And then from there, you just have to do the integral of cos squared theta. This is integral 0 to pi over 2 cos squared theta d theta, which is done using a half angle identity, right? That's 1/2 integral 0 to pi over 2, 1 plus cos 2 theta d theta. And what you'll see is we're going to get that same answer out. I have 1/2. Antiderivative of 1 d theta is theta. Antiderivative of cos 2 theta is sine 2 theta over 2. And we evaluate this from 0 to pi over 2. So this will be 1/2 times pi over 2 plus the sine of 2 times pi over 2 is pi, all divided by 2, minus 0 plus the sine of 0 over 2. And you know, like always, this shit's all 0. This thing is 0. So what we get here is just 1/2 times pi over 2, which is pi over 4, as promised. Okay? This is called Trig-Sub. It's a little tricky, but the main thing that's going on here is going on way up here. It's this, specifically this turning into this. It's a consequence of the Pythagorean identities. If you have 1 minus x squared and you replace x by sine theta, then that will become 1 minus sine squared theta, which is cos squared theta, and then the square root can cancel. So Trig-Sub is usually a trick for getting rid of square roots. That's the way to think of it. Square roots don't work nicely with addition and subtraction. If you have some addition and subtraction going on underneath your square root, you really want to get rid of that square root because there's not any nice way to distribute the power. You know, that's this note that we began with, right? Up here. These sort of things don't work. So how do I get around that? Well, I need some other way to kill square roots. And from here to here, I've been able to kill the square root. So that's what Trig-Sub does. And it's very convenient that we have a few different forms of the Pythagorean identities, because each form of the Pythagorean identity will be useful for killing a different kind of square root. So square roots we hate in integrals, and subs that kill them. Some square roots we hate in integrals are things like square root of a squared minus x squared. I really wish it was a minus x, but it's not. The sub that kills this is x equals a sine theta. Because you would have a squared minus a squared sine squared theta. You can factor out an a squared, and the 1 minus sine squared theta that's left over would be a cos squared theta. Another kind of square root that we loathe is the square root of a squared plus x squared. Again, I would love it if this was a plus x, but it's not. But there is a substitution that will make it go away, and that's x equals a times the tangent of theta. And then finally, there's the square root of x squared minus a squared. These can be murdered using the substitution x equals a times the secant of theta. And I just want to show you why. So this is this little table right here, I call the Trig-Sub Bible. If you see one of these, you want to make one of these, because these substitutions get rid of all these square roots. Why does this work? Well, if x is equal to a times the sine of theta, then the square root of a squared minus x squared is the square root of a squared minus a squared sine squared theta. If you plug in a times the sine of theta for x, the square of that is a squared sine squared theta. You can factor out an a squared, and what's left there is 1 minus sine squared theta, which is the square root of a squared cos squared theta, which is just a cos theta. Again, assuming that cosine is positive, which we will do. If x is equal to a times the tangent of theta, then I should really have a comma here, then the square root of a squared plus x squared becomes the square root of a squared plus a squared tan squared theta, which is the square root of a squared times 1 plus tan squared theta, which is the square root of a squared times, well, 1 plus tangent squared, tan squared plus 1, that's secant squared. So this becomes the square root of a squared secant squared theta, which is a secant theta. Again, assuming the appropriate domain stuff to make sure that the absolute value of secant is just secant. And the same thing works for the last guy. If x is equal to a times the secant of theta, then the square root of x squared minus a squared becomes the square root of a squared secant squared theta minus a squared. Factoring the a squared inside, we get a squared times secant squared theta minus 1 under the square root, which is the square root of a squared times tan squared theta, which is a times the tangent of theta. So any square root that looks like one of these can be turned into a plain old trig function by making the appropriate substitution. this is our little intro to Trig-Sub. The table at the top, you need to remember. This, make sure this gets into your notes, make sure it gets in there nice and clear. This is very important. A here is a constant. In the example we did, A was 1. All right, we did the square root of 1 minus x squared. If A was, if you had the square root of 2 minus x squared, then A would be root 2. If you had the square root of 4 minus x squared, then A would just be 2. If you had the square root of 9 minus x squared, A would be 3, and you would substitute x equals 3 sine theta. We'll do lots of examples with this stuff next week, but I wanted to introduce it to you now. In particular, I want you guys thinking about this. I want to make sure that you're really comfy with these simplifications. So are there any questions on how I'm simplifying this line? Okay, any questions on how we're simplifying the other lines here? The kind of magical or powerful step is 1 minus sine squared is cos squared. 1 plus tan squared is secant squared, and secant squared minus 1 is tan squared. It gets rid of the addition or subtraction by replacing it with its single Pythagorean equivalent.
Professor Faustiger?
Yeah.
So we don't have to worry about like putting absolute values around cosine, secant, or tan, because if it's a definite integral, we're gonna have the bounds that I guess don't make us worry about that.
Exactly. Yeah. So for example, in this first guy, I would never ask you to integrate this over any x range that corresponded to a theta range for which cosine was negative. It's true that in practice, out there in the real world, if you need to make these substitutions, you need to be a little bit careful because this should be an absolute value of cosine theta. But for our purposes, you don't need to worry about that. I will design the problem so that you don't need to worry about that. And really out there in the real world, you'd be surprised. Anytime you do have a situation where that absolute value can cause you trouble, you can use a symmetry argument to get around it. So yes, it's true. We really should have absolute values here if we're being careful. But it's easier to learn how to do this stuff if you don't worry about that. And in practice, there's always a way to get around it.
Okay, thank you.
Yeah, of course. Other questions or comments here?
Can I see a picture of like the first page, because I came back from the break a little too late, so I didn't get like the first part.
So here's where we started. Let me, here, I will zoom in on a part of this. Here's that sort of first bit.
Okay, thank you.
And then the way we proceeded from here was like this.
Okay, thank you.
All right. So that's all I really wanted to do for you guys today in the lab. If you had questions, though, that you wanted to ask in office hours and weren't able to, or any particular homework problems that are driving you nuts that you'd like to look at together, I'm happy to do those. We have some time left.
Are we gonna talk about the one case of like secant and tangent that aren't pretty, where we would have to use IBP or like looping integrals?
Yeah, let's look at a few of those, right? So we've seen one of them, secant cubed. Let's look at a few other problems like that. So the scary case there is where the power of secant is odd and the power of tangent is even. So one example there could be secant theta times tan squared theta d theta. The truth is I can only ask so much of you guys here. Just like how sort of the combined powers for the even sine and cosine guys shouldn't exceed 6, the combined powers for the nasty secant tangents really shouldn't exceed 3. So besides secant cubed, the only integral like that you're really going to encounter is this one. There's a few ways to attack this. One way is to jump in and turn it immediately into an integral of secant and secant cubed. That's a little bit lame. So another approach, if we want to see something kind of novel, is to rewrite this as secant theta tangent theta times tangent theta d theta. And then I can run some IBP. So these all require integration by parts. And the way I would do this is by running this with u equals tangent theta and dv as secant theta tangent theta d theta. So du here would be secant squared theta d theta, and v here would be the integral of secant tangent. Well, who differentiates to secant tangent? That's secant theta. And you'll see that there's really no getting away from the connection to the secant cubed integral. Secant cubed is kind of the Mac daddy of all of these. I'll have u times v, which is secant theta tangent theta, minus the integral of v du, which is secant theta times secant squared theta d theta. At this step, I could say, oh, this is secant cubed. I know how to do that, and jump in and attack that on its own. But the more natural thing to do here is to try and make this integral loop, to try and get this guy to show back up. So the trick is to replace secant theta by his Pythagorean equivalent. So secant theta is the same as tan squared theta plus 1. So in this integral, I will replace secant squared by tan squared theta plus 1. And now if I distribute this secant term, I'll get the integral of secant times tangent squared plus secant, like this. And then just like I do with the secant cubed integral, I need to split this guy up and distribute this negative. So you got to be really careful there. You're going to get secant theta tangent theta minus the integral of secant theta tan squared theta d theta, which is my original integral, minus the integral of secant theta d theta. And at this point, the integral has looped. If I want to summarize what we have so far, I can say, so integral of secant theta tan squared theta d theta is equal to secant theta tangent theta minus integral secant tangent squared minus the integral of secant theta. And this is the integral looping. So I can add this portion back over to the right-hand side. So this implies that 2 copies of the integral of secant theta tangent squared theta d theta is equal to secant theta tangent theta minus the integral of secant theta d theta. And at this stage, I replace the integral of secant theta by what it is. I know this. What is this?
ln of absolute value secant x plus tan x.
Yeah, or a secant theta plus tangent theta. Yeah, so this would be
Oh yeah.
2 secant theta tan squared theta d theta equals secant theta tangent theta minus the natural log of the absolute value of secant theta plus tangent theta. And this is where I slap on my plus c. And then we divide by 2. And as much as we like to talk these up, there's really not much more I can give you because these problems get out of control so fast. And you may notice that this answer is very similar to the answer for the integral of secant cubed. The only difference is that the plus became a minus. If we start increasing the powers, like if I make it secant cubed times tangent squared, or secant times tangent to the 4, if I start jacking the powers up, these really do get out of control very fast. So honestly, the only 2 integrals of this sort that I could even ask you to do are this one, secant times tangent squared, and the other one that we've seen so far, which is secant cubed. Really anything else is kind of too much. So I would say make sure you're comfy with the secant cubed integral. If you're comfy with that one, then you'll be comfy with this one because this is really the same trick. And make sure you're comfy with the e to the x cos x type integrals, the damped harmonic oscillator stuff. As far as looping integrals go, those are really the only ones I can hit you guys with in this class. It's true that the larger odd powers of secant or the larger combined powers of these guys can be exciting problems to solve. But it really is this same trick, whether you're looking at secant to the 5th or secant to the 7th, or like secant cubed times tangent to the 4. All of those are done the same way. You run IBP once, you apply a trig identity, and then the problem gets knocked back to something like this, where you have your original integral and then an integral of an odd power of secant, one down from the combined power you had here. So if I had started with secant cubed times tangent squared, this would be a secant cubed instead of a secant. If I started with secant cubed times tan to the 4, this would be a secant to the 5 here. You would still get your original integral here. You would still get a secant tangent here. And then you would just have to continue chipping away at this guy. Does that make sense?
So tangent just goes down a power each time you do IBP, like on the last integral.
Well, so my original integral will show up here exactly as it was. And then this, if you set up your IBP the way I did, will be an odd power of secant, one odd power smaller than the combined power here. So the combined power here is 3. The next odd number under 3 is 1. If the combined power here had been 5, then this would be a secant cubed. And everything else would be the same. This would be my original integral. This would be a combination of secants and tangents.
Okay, thank you.
Yeah, of course. Is there anything else that you guys would like to look at from the homework or anything you wanted to talk about in office hours that didn't get a chance to?
Can I ask questions about this problem?
Yeah, of course. Yeah.
How did you go from the 3rd step from the bottom to the following step?
From here to here?
Yeah.
So from here to here, I just plugged in for the integral of secant.
Which we should just know.
Yeah, this is one that we should just know. The integral of secant is the natural log of secant plus tangent. That's one that we do want to commit to memory. Remember the way we did this, you multiply in here by secant plus tangent over secant plus tangent, and then substitute for the denominator. It's a weird thing, and we don't use that trick anywhere else. So I would say, I'm not a fan of saying you need to memorize things, but this is one thing I would say is worth committing to memory. I will, after we talk about partial fractions, I will have another way to attack the secant integral, but it's still not short. You know, it's still kind of a long process. And so really the best way to handle these is to just remember them. Any other questions on this particular problem? Any other questions from homework problems or anything else that you guys would like to look at while we're here?
Personally, I'm going to keep chopping away at the homework, and eventually I'll run into problems that just stump me. And I'll probably come in for office hours like tomorrow, just because this is pretty challenging.
That's fine. Yeah, of course. So if there aren't other questions, let me say a few things in parting them. First, again, I really am sorry if you guys tried to come to the office hours today and weren't able to get in. That sucks. I'll look in to see what happened yesterday, since apparently there was some trouble getting into yesterday's office hours, which was supposed to be running like normal. But in general, if you want to talk to me about a problem, or if you're struggling with a problem and you're having a difficult time getting the help that you need, feel free to email me. Don't be shy about it. You can take a picture of your work and send me that as an attachment. I do check my email through the day. I check it on my phone, even in bed as I'm getting ready to go to sleep at night. So if you send me something like that, I can give you a quick reply with a little hint or a little tip to push you in the right direction. So never be shy about asking for help. And one of the best ways to ask for help is to share your work with me. Show me what you've tried. And I'm really, really into looking and seeing what you're doing. That way I can give you maximally useful feedback. And the other thing is, I do set aside 5 hours a week to spend on custom office hours, one-on-one office hours. And a handful of people from this class have requested those, and we've done them. They've been nice. You can always do that. So if you can't come to my regular office hour, or if my regular office hour doesn't work out for whatever stupid reason, don't hesitate to send me a message saying, hey, Professor Fausner, can we meet at this day and this time? Best if you give me like 2 or 3 times that work for you, so I can see what fits my schedule. And I'll reply back with a link to a Zoom meeting, and then we will meet at one of those times. And the one-on-one meetings can be more productive because you don't have to wait while I bounce around between different people. So if you do want to ever talk about solving problems or anything related to this class, don't hesitate to email me. Don't hesitate to ask for an extra office hour. I build time into my schedule to accommodate that, and I'm really happy to do it. It's fun for me. It is. This is genuinely what I love to do. So don't hesitate. Don't suffer in silence. This is what I'm here for.
I have a quick question on one of the homework assignments.
Yes, please. Yes.
I mean, it's working out a problem. Do you just want me to like read you the question?
Sure. Yeah, we can do it like that. Sure. What do you got?
So it's integral and then fraction bar.
Okay.
Then on the top, it's gonna be 5x e to the 2x. And then the bottom is gonna be parentheses 1 plus 2x close parentheses squared dx.
This is a neat one, and I think this is one that we did in class the other day, but we can take another look at it because it was challenging then, and it's still challenging now. First thing I would do is bring out the 5. And I confess, when we did this in class the other day, I didn't see the path right away. This is not easy. But if you think about the derivative of the top, this would be a product rule derivative. The derivative of the top here is neatly related to the bottom. So the way to attack this is by parts, where u is x e to the 2x, and dv is 1 over 1 plus 2x squared dx. This is well outside of our Lipet rule, right? This does not fit into our Lipet rule at all. But if we calculate du, this is a combination of product and chain rule stuff. So I'll differentiate the x, that's 1, and leave e to the 2x alone. Then add that to what I get when I leave the x alone and differentiate e to the 2x. That's 2e to the 2x. So du is all of this times dx. And then to calculate v from dv here, I need to do a little integral off to the side. So v is going to be the integral of 1 over 1 plus 2x all squared dx. And we can do this with a little substitution. Z equals 1 plus 2x. dz is 2 dx. So this is going to be 1/2 integral 1 over z squared dz, which is 1/2 z to the negative 2, integral z to the negative 2 dz, which is 1/2 z to the negative 1 over negative 1. So my v here is negative 1 over 2 times z, which is 1 plus 2x. It's very tricky. And this IBP table is anything but clean. But this is the nicest way to do this, as far as I'm aware. Calculating this antiderivative, little bit of work. Calculating this differential here, a little bit of work. But if you factor the e to the x out of this, the e to the 2x, what's left here is 1 plus 2x dx. So what we get is that 5 times the integral of x e to the 2x over 1 plus 2x squared dx is equal to u times v. So that's x e to the 2x times negative 1 over 2 times 1 plus 2x minus the integral of v times du, which is negative 1 over 2 times 1 plus 2x times e to the 2x times 1 plus 2x dx. Oh, and there's a 5 out front of all this, right? Yeah, 5 in front of everything, because I brought out the 5. It's a weird problem. It really is. But it's a cool problem. So from here, we have 5 bracket x e to the 2x, I'll put the negative here, over 2 times 1 plus 2x. This minus and this minus will make the integral positive. The 1 plus 2x here, I'll write everything out. We'll have e to the 2x times 1 plus quantity 1 plus 2x over 2 times quantity 1 plus 2x dx. And you can cancel these. So it happens to be the case that the product rule derivative of this thing cancels beautifully with the integral of this thing. You can pop out the 1/2. You get 5 times negative x e to the 2x over 2 times 1 plus 2x plus 1/2 times the integral of e to the 2x dx. And now this guy is a little micro u-sub. So this is going to be 5 times quantity negative x e to the 2x over 2 times 1 plus 2x plus this 1/2 together with the 1/2 that comes from my little micro u sub there will give me 1/4 e to the 2x. And then we slap on our plus c here. Yeah, this is a genuinely challenging problem. Not at all obvious how to get started. The intermediate steps, just filling out the IBP table, are quite tricky. But after you get the right combination, the right choice of u and dv, which again is this, it does come out really nicely. And this is a good example of a problem on which LIPET does not help us, doesn't help us at all.
Sorry, what was the micro u sub again?
So the integral of e to the 2x, you make a little tiny u sub in here, like I guess I'll call it w. W equals 2x, so that dw is 2dx. And then the e to the 2x integral will become 1/2 integral e to the w dw, which is 1/2 e to the 2x. So this piece is 1/2 e to the 2x. The two 1/2s make a 1/4. It's very sneaky, very sneaky. I'll say this, I've spent my entire professional life integrating functions, right? As an analytic number theorist specialized in elliptic functions, this is kind of what I do. And even I didn't spot this. I didn't spot this right away. It took me some time. It's not an obvious move at all. But it is a cool thing. And if we spend enough time, there's only so many combinations we can try to pick for u and dv. We spend enough time cycling through the possible combinations. As soon as you see this, as soon as you see that the derivative of that choice of u contains a 1 plus 2x, that should tell you, oh yeah, I'm really on the right path because I've got this other 1 plus 2x factor downstairs that I'm just dying to get rid of. So as soon as you calculate the derivative of this as this, you should be able to smell that you're on the right path. But I'll say again, not an easy problem.
Thank you. And I have another question on one more problem, if you don't mind.
No, yeah, happy to do it. That's what we're here for. Yeah, what's up?
It's the integral of ln x, all that squared dx.
Sure. So there's a few problems involving natural logs in the homework. And of the two, right, the other one is like the natural log of the square root of x. That one's actually really easy if you use your rules for logarithms at the start. This one, we just have to handle it raw. So this is going to be IBP with u equal to the natural log of x squared and dv equal to dx. This one does fall to LIPET, right? We've got a log function, so we should pick that for our u. The log function here happens to be squared. There's no getting around it. So this is straight up IBP. My du, I need to calculate using the chain rule. This is 2 times natural log of x all raised to the 1 times the derivative of ln x dx. So the chain rule work to get du here is a little bit subtle. And then v, the integral of dx, is just x. So here's my IBP table for this guy. And if I follow the IBP formula, I have u times v. I'll write the x up front just because it looks better. Minus the integral of v du. And within this integral, everything is being multiplied. So the x here and the 1 over x here will cancel. And I get x times the natural log of x all squared minus 2 times the integral of the natural log of x dx. And the net effect of this run of IBP is to take the power down by 1, right? I started with a natural log all squared, and now I have a natural log. So if I run IBP one more time, remember the integral of ln x, this was one of our kind of first IBP problems. So this requires one more run of by parts. Again, following Lipet, u is going to be the natural log of x. dv will be everything else, which is dx. Here du is 1 over x dx, and v is x. So our second IBP table looks like this. And out comes x times the natural log of x all squared minus 2 times, and now I need to open up a big paren. I'm about to replace this integral by a difference of 2 terms, right? uv minus integral of v du, and that 2 belongs to both of them. So this open parentheses here is very important. Now u times v is x times the natural log of x minus the integral of v du, x times 1 over x dx, and I can close that big paren. The x's here cancel as well. So I get x times the natural log of x squared. I'll distribute the 2, minus 2x ln x. Cancel the x's and distribute the 2. We give me plus 2 times the integral of just dx. And the integral of dx is just x. So this is x times ln of x squared minus 2x times the ln of x plus 2 times the integral of dx. Well, the integral of dx is just x. And now we add on our plus c. This is another good problem. It's possible to rewrite this integral as x squared times e to the x, or I should say u squared times e to the u with a little substitution. But it's more satisfying, I think, to jump in right away with just the IBP.
Got it. Thank you so much.
Of course, of course.
So if something has like a power, like following Lipet and what our function has like a power attached to it, just do IBP with the power attached to that function.
Yep, yeah, here, so kind of when I'm picking u following Lipet, if there's a monomial that has a natural log in it, then that whole monomial will be u. And I would follow that rule all the way down. If there's a monomial that has an inverse function in it, I would pick that whole monomial to be u. So even if it's not just a logarithm, if it's any monomial term with a logarithm in it, I would consider running that as u. There are other ways you can try this. You could try running this with u equal to ln x and dv equal to ln x dx. That will also work. But then your dv to v step would require an integration by parts on its own, which is a little bit sneaky. So many of these things have multiple ways you can solve them. And it's kind of like, you know, you're going on a walk through the woods and you find yourself walking down a path that gets scarier and scarier. You've got cobwebs and you hear witches cackling in the distance and there's a trail of blood leading off into the dark. If shit starts looking bad, maybe go back and try something else. But you've got many, many different paths which could get you there. And even some of the scary paths work. This, I think, is the simplest path for this problem. But I can right away see at least 2 other paths that would work. Again, the other options here that could work, if you wanted, as your first step, you could run IBP with u equal to ln x and dv equal to ln x dx. This would work. And then the other option you could make, so you need to calculate du and you need to calculate v. The trick is that the dv to v step here requires an integration by parts. So that's kind of, you know, getting a little bit scary. The other option is to substitute z equals ln x. dz would then be 1 over x dx, but this starts to get a little scary too, because now you don't have a 1 over x in here to make this substitution easy. So this would become x dz equals dx, which is equivalent to saying, well, if z is ln of x, then x is e to the z. So this would be e to the z dz equals dx. And this substitution here would change your integral into z squared e to the z dz. So all three of these paths are viable. This alternate IBP is viable, but the dv to v step here requires another IBP. I think this is the most natural one. If you do try to make the substitution that I outline here, even after doing this, this still requires 2 runs of integration by parts. So all that work really doesn't get us anywhere. So this is the solution that I recommend.
Can we do 23 on this week's homework?
Yeah.
It has like sine within x, so I want to see how we do that.
Well, the sign kicking me out again. And of course, no, wrong class, sorry. So we wanted to see 23, right?
Yeah.
This one does require a substitution before we get started. So we want to integrate cos theta times the 5th power of cos of sine theta. Can anyone suggest how to get started here?
Probably distribute.
Well, it's not anything I can distribute. This.
Convert cosine to sine.
Something to do with the relationship between sine and cosine. Let me try rewriting this in a more evocative form. This is cos to the 5th of sine theta times cos theta d theta. So I'm just shuffling this cosine over here to sit next to the differential to remind us of something we did on the earlier problems.
So if we want to find cos theta, d theta, we want to like substitute that. So we should differentiate sine.
Right. The derivative of this is this. So if I make the substitution, z equals sine theta, then dz is cos theta d theta. This is a classic U-sub problem, right? I've got an inner function and an outer function, and the derivative of my inner function happens to be sitting right here. So under that substitution, this will become the integral of cos to the 5th of z dz. And now I'm looking at just a regular trig integral. So from here, if we can remember how to handle just the regular trig integral, we're good. How do we integrate the 5th power of cosine?
Probably start setting some stuff apart and converting it to sine.
Good, yeah, it's an odd power, right? So I'd rewrite this as cos to the 4 of z times cos of z dz. And you'll start seeing why it's so damn important that we write the inside of our trig functions, not just cos, not just sine, but cos theta, sine theta, cos z, because you could get really confused here otherwise. Now that I have cos to the 4 of z times cos of z, I want to substitute for sine of z. So I'm going to rewrite these 4 powers of cosine. This is cos squared of z all squared times cos of z dz, which is integral 1 minus sine squared of z all squared times cos of z dz. And from here, the move is to substitute something like w equals sine z. dw then is cos z dz. And this will be integral 1 minus w squared dw.
Hey, could you leave that up for a little bit? I'm just trying to absorb what you've written so far.
Yeah, of course.
Are we gonna have to plug back in W and then go back to their Z function and plug back in Z?
Yes, we will. Yep, that will be necessary. Because it's an indefinite integral, we need to give our answer in terms of the variable theta, which means we're going to have to chase back through 2 of these substitutions. But that part won't be hard. Now that we're here, we have a polynomial. We just need to expand it out. So this will be 1 minus 2w squared plus w to the 4 dw, which will have antiderivative w minus 2w cubed over 3 plus w to the 5 over 5 plus c. And then we chase our way back up. So w is sine z. So it's sine z minus 2 sine cubed of z over 3 plus sine to the 5 of z over 5 plus c. And then in my very last step, I use the fact that z is sine theta. So this is going to look like, let's see here. The z was sine theta, that was the sub we made. So this is sine of sine theta minus 2 sine cubed of sine theta over 3 plus sine to the 5 of sine theta over 5 plus c. Pretty gnarly, right? This is a good problem.
Thank you.
Yeah, of course, of course. Yeah, these are fun. So this is a good example where we do one substitution, which turns a really weird looking problem into a regular trig integral problem. But then that trig integral problem requires another substitution. So at the end, we have to chase back through 2 substitutions. If this were a definite integral, it would be a great example of why you should always change your bounds, because you could skip all this shit, right? You could just evaluate this between whatever your W bounds were. But it's an indefinite integral. There's no harm in doing it like this. I think for a lot of people, it's less intimidating in this way. Any other questions that you guys would like to take a look at before we go? We've got a few more minutes left here.
How about 24
Sure.
on the homework?
So cos squared tan cubed. Yeah, let's take a look at this. This doesn't look like our normal stuff. Has anybody tried this one yet? It's not a sine cosine integral, and it's not a secant tangent integral. But we can rewrite it as such. First, I would break everything down into sines and cosines. So tan cubed is sine cubed divided by cos cubed. And now cos squared upstairs and cos cubed downstairs, they can talk to each other. This is going to be sine cubed divided by cos x dx. And if I wanted to, I could rewrite this as a secant tangent thing now. But I think more clever than that is to look for a substitution.
U equals sine.
So let me try something like this. Because I don't have a cosine term upstairs to play with. If I had an extra cosine term upstairs to play with, then I would say, let's try to substitute for sine. Because the cosine is what I would need to group with the differential to make that go through. But I do have an extra sine term upstairs, right? I've got sine cubed upstairs. So I can grab one of those off the top and set it next to dx. And what this hints at is wanting to sub z equals cos x. Because dz then would be negative sine x dx, and I've got a sine x dx here. The problem is with the sine squared. So before I can push that substitution through, I have to rewrite the sine squared as 1 minus cos squared. So I have 1 minus cos squared over cos times sine. And now this integral is ready for this substitution. It will become integral 1 minus z squared over z times negative dz. And we can pop the negative 1 out. So this will be negative integral 1 minus z squared over z dz. How do we do that?
Can you do it like 1 over z minus z squared over z, which is just z?
Very good. Yeah, exactly. We'll just split it up. We'll just use some algebra from here. So I'll leave my negative out front, and inside I can split this up as 1 over z minus z squared over z. And just like Kaylee said, this is going to be 1 over z minus z. So I'll have negative integral 1 over z minus z dz. The negative will stay. 1 over z integrates to the natural log of the absolute value of z. Z itself integrates to z squared over 2. And I add on my plus c. And then the last thing to do is to go back to my original variables. So I'll distribute the negative in the same step. Negative natural log cos x plus cos squared x over 2 plus c. And the negative natural log cosine is suggestive of the idea that we could have written this in secants and tangents and maybe tried some IDP or something. But I like this approach. I think this is, again, the natural approach here. From this step, we moved up here. All right, I do think that's about all we have time for today. So I'm going to go ahead and wrap things up here. Please continue working on these trig integrals. The better you get at trig integrals, the easier time you will have with Trig-Sub. Trig-Sub tends to be one of the harder sections on exam 1. So next week, we're going to start with Trig-Sub on Tuesday. And I think we will finish Trig-Sub on Tuesday. It's not necessarily a hard section to introduce or to lecture on. It's just one of these things that you really need to practice to get comfy with. And it's not the Trig-Sub itself that you need to practice and get comfy with, it's the trig integrals themselves. So please invest the time in this week's homework. Make sure you spend a meaningful amount of time working these problems. Work them until you really understand them. If you finish the homework problems that are assigned and you're still feeling a little bit short of understanding, open up the textbook. There's lots of problems here that I didn't assign because I start to feel bad when I see that number climbing too high and you guys stressing out over it. So come in here and look at some of the extra problems that are here. There's lots of them, right? Many, many problems here for you to work. So I would work these 7.2 problems until you're really comfy with them. And that will make 7.3 much, much easier.
Yeah, I'm just trying desperately to finish the homework, so I'll see you tomorrow, Professor.
Sounds good. Yep, remember it. Regular office hours tomorrow, and you can always email me pictures of your work. I'm happy to help you that way too. Alrighty, gang, I hope you have a wonderful rest of your afternoon. Thank you so much for hanging in here. I know these Thursdays are long, but you've all done a wonderful job. Just keep working hard and things will be okay. Next week, I'll talk to you a little bit about exam 1. We are getting close. I think by next Thursday, we will be ready to schedule exam 1, and then exam 1 will likely be the Thursday after that. But don't set it in stone as that just yet. It may change a little bit, but most likely exam 1 2 weeks from today. All right, take care, gang, and I'll see you on Tuesday.
All right, have a great day, Professor. See ya.
Bye, guys.